Today we're going to talk about hyperbolas. Just like ellipses, there's going to be some similar relationships and things, but so let's just dive in and take a look at something. So the definition of a hyperbola is the collection of all points so that the difference between their distances from two fixed points, foci, is a fixed constant number. So what that means, before we take a look at this applet, which I encourage you to pause and do so on your own, it's a really great applet, is that if you call this distance d1 and this distance d2, then the difference between those, d1 minus d2, will equal some fixed constant number, some constant number that does not change. And it turns out that it's the length of this transverse axis between the vertices. But for any point, if you change this. So let's take a look at this applet real quick and see if we can illustrate that relationship. Okay, so we've got our foci, we've got our vertices, and we've got this line that goes sort of through the quote middle of the hyperbola in the perpendicular manner, so to speak. We'll call that the transverse axis going through the vertices. I could move this point anywhere around, and you can see the distances from that point to the respective foci changing. So let's see if we can illustrate the fact that the difference between these two distances is always equal to that one fixed value, the distance of that transverse axis between these two. As you drag these, I'll just have a look at it. So yeah, reset. So as I drag this slider, it's going to take and to put the two distances, and it's going to put one on top of the other. Then you can visually see the distance there. And the idea is to emphasize that difference, subtracting the two differences, gives you the distance between the two vertices on the transverse axis. And instead of making you watch lots and lots of examples of these, we'll just do two and encourage you to mess with it yourself. It's a really great applet. So there we go. There's the big long green distance. There's the big long red distance. And sure enough, take the red distance off the green distance, and you've got that distance between the two vertices. So the collection of all points, the difference between their distances from two fixed points, foci, it remains a constant number. That's the definition of a hyperbola. So let's take a look at kind of anatomy of a hyperbola, so to speak. So I've got one graphed here, and the link is right there if you like. But just like our discussion for ellipses, there are going to be a bunch of different distances that we're going to label here. And so there's this point right here at the origin. We're going to call that the center of the hyperbola. That's what I'm going to call it. And so the distance from the center to the vertex over here in the x direction, well, when we were dealing with ellipses, we called the x direction A and the y direction B, and we're going to do the same thing here with hyperbolas. However, again, note that the text reverses that relationship depending on whether the hyperbola opens up or down. I just think it's easier to always kind of draw the picture and derive the formula myself rather than memorizing a bunch of formulas. So the distance from the center to the vertex is what we're going to call A. In this instance, it happens to be 4. So, all right, so there's no vertex, so to speak, in the vertical direction for this example, but that box kind of defines, and the asymptotes that go through the corners of these boxes, that box sort of defines this hyperbola in its own way. So we're going to call the vertical distance here B, and that's going to be B equals 3 in this instance. And then just like ellipses, the distance from the center to this point over here being a focus is going to be C. In this case, it happens to be, I don't know what it is. I've lied on all kinds of things. Please forgive me. Okay, so, but let's not even put the numbers in here. Let's just label them with with what we're going to call them. A for the x direction, B for the y direction, and then the distance from the center to the focus is always called C. And since there's symmetry involved, those are all the same in all the other directions. What else we got in this picture? Well, I said it, but I didn't label it. we've got these two kind of diagonal lines that go through this box, which kind of define the hyperbola, and that the curve of the hyperbola approaches these asymptotes. So these are asymptotes. And if you know those asymptotes and the focus and the vertex and the center, you know quite a bit about your hyperbola. And then some texts call in this case, it's the x-axis goes through the focus and the center and the vertices. Some texts call the entire thing the transverse axis. And as you saw, that applet just referred to just the distance between the vertices as the transverse axis. We're going to call it the entire axis that it goes through the center of all these points. The transverse, and I always mispronounce that. The transverse axis here. Okay, so just like ellipses, we have an A-B-C relationship. And that relationship is mirroring the image we have above. We've got that box, and you've got a focus and vertex in the center, and because symmetry, you have it on both sides. And, well, the distance from the center to the vertex here is your A. And the vertical distance from the center to the sort of top of the box that gives us our asymptotes, which defines this, is B. And then, just like ellipses, the distance from the center to the focus, the C distance, connects those two points. This is also C. And so for a hyperbola, we actually have the standard Pythagorean labels. So if you know one or two of the others, you can find the third. Again, just draw the picture, and this is always center to focus. Same as for ellipses. All right, so let's take a look at the general formula or equation for an ellipse. And here we have it centered at the origin. And so you have x direction, which is called sideways ellipse, if you will. What can't be here? Well, so if x was 0, so notice, no, x is not allowed to be 0. Else, we would have negative y squared over b squared equals 1. And that would be that wouldn't be a hyperbola. That would be some kind of a parabola. So since you can't have that first term be missing, x is not allowed to be 0, this tells us that we never cross our x-axis. And so from that, we know that we have a hyperbola that will cross the y-axis. And so if you draw this as a picture, wait, I'm sorry, I'm saying the wrong things. Since x is not allowed to be 0, that relates not to the y-axis. Where is x not equal 0? That's the y-axis there. X equals 0. So this thing will never cross the y-axis. Okay, so how could you possibly draw a hyperbola centered at the origin that never crossed the y-axis? It necessarily has to open up left and right. For the same logic, similarly, you can't have y. The y term can never disappear for this one. Otherwise, if that did happen, you would get negative x squared over a squared, which equals 1. And again, that would be some kind of a parabola because you only have one term squared. And so y is not allowed to be 0, means you never cross the x-axis. And if you never cross the x-axis, but you have a hyperbola centered at the origin, well, the only way the hyperbola can exist is if it opens up and down, so to speak. And so that's kind of a justification for why those formulas are the way they are. Okay. So let's talk about this distance from the center to the foci, C. It's just like ellipses. And so we're going to actually review ellipses here. The only difference is that our triangles are labeled a little bit differently. So for an ellipse, we had two foci in the middle, and we had vertices on the outside, and then we had minor vertices here. Oh, and I'm going to try and use the same colors here. So here, I need the center in there. The center in there. So here, the distance from the center to the focus was C, and then the distance in the x direction was A, and the distance in the y direction was B. And then we learned that this distance connecting the focus and the minor vertex here was the same as that longer distance between the center and the vertex. So it's not just like ellipses, but there's a lot of parallel here. Hyperbolas. Whereas with a hyperbola, what do we have? Well, it's defined kind of by a box, which has two asymptotes in there. If you're going to draw it moderately well. Okay, and what are our relationships here? Well, I guess I should draw our hyperbola. Let's say that we have it opening up this way. No, we did one of those, so let's do one of the other ones. We'll open this one vertically. Okay, so x direction in blue, we're always going to call A. From the center to the end of this box, there's our A. Now here, again, draw it well if you're going to draw it. I'm sorry. That means these are the vertices, and so our hyperbola opens up and approaches the asymptotes. So now that vertical distance, that's going to be green. That's going to be our B distance there. And then where's your focus with a hyperbola? Well, the focus for a hyperbola is actually out here. And that distance we draw in red always from the center to the focus here is this red distance. But that's the same distance between these minor vertices. Is not the wrong term here because it only has two. But you could sort of imagine this point right over here as kind of an unconnected minor vertex. Well, the point is you've got yourself a Pythagorean theorem, a right triangle that you can use the Pythagorean theorem. And with hyperbolas, you always have this standard Pythagorean theorem lettering, whereas ellipses you will not. Okay, so I'm going to try and stick with what I've been doing using A to be blue for the x direction, B to be green for the y direction, and C to be red for the distance between the center and the focus. So it could be either in the x or the y direction, depending on how the hyperbola opens. But the game here that we're going to start off with is kind of analyzing a hyperbola is to find the box that generates the asymptotes using the A, B, and C, graph the hyperbola, and then identify the parts. Advice here is using graph paper is really helpful. We won't here because that's just what we're going to do. And I'm going to stop this video and start a new one with an example.